Hello everyone, my name is Hasti and I'm a PhD candidate working with Glenn Kapsak and Nikki Nelson at Swinburne University. Today I'm going to talk about our recent published study in Disentangling the origin of an observed intervening gas shared in a group using KCWI. CGM or circumgalactic medium is the interface between interstellar medium and intergalactic medium that harbors multi-phase diffuse gas. As shown in this figure, gas accretion along cosmic filaments not only provides fuel for star formation, but also adds angular momentum to the disk. Stellar winds and supernovae feedbacks will be ejected from the galaxy through the outflows, and this outflowing gas may eventually rain back down into the CGM and be recycled. These features make the CGM a great laboratory to study the baryon cycle of galaxies that play a prominent role in their formation and evolution. Many studies using quasar absorption line technique have investigated the CGM of isolated galaxies and found that the CGM gas is not isotropically distributed around the galaxy, whereas the majority of gas could be found along the major axis of galaxy as a trace of inflows and also along the minor axis of galaxy, tracing the expelled outflows. Also, this technique has been used to study the relative kinematics between absorption line and the host galaxy. In fact, comparing the CGM absorption kinematics with galaxy rotation velocity could imply whether the observed absorption co-rotates with the galaxy with an extended disk-like structure that accretes onto the galaxy or not. In this work, we have used the quasar absorption line technique to study the impact of environment on the CGM of a particular group sample. CGM properties in group environments are more complicated and gas distribution is more extended. It's because the group environments are affected by various processes like intergalactic gas transfer, mergers, or tidal streams. Historically, many surveys looking for CGM host galaxies are not spectroscopically complete, whether to large impact parameters or to low luminosity. This is because it's been time intensive to obtain a spectra of every galaxy in each field with a single slit spectrograph. The power of IFU and instruments like KCWI and MUSE are quickly changing this. It means that when previously surveyed fields are observed with these IFU, new galaxies are quickly identified, and the picture of an absorber corresponding to a single isolated galaxy is looking to be more rare than previously thought. As an example, this field has a trace of absorber already associated to an isolated galaxy, which is marked here. This field was reobserved with MUSE, and 5 new galaxies were detected at the redshift of this absorber. And here is an image of the quasar field that we have explored in our work. This HSD image shows the field of a quasar with a trace of intervening absorption system at redshift 0.39 that previously thought to be CGM of an isolated, massive star-forming galaxy with strong outflows, studied by Muzahid et al. This galaxy is marked with cyan on all the figures. In this plot, we can see this multi-phase absorption system observed in the background quasar spectra. The system includes both low ionized phase of gas with low metallicity and only 3 components like magnesium 2 and carbon 2 ions, and also high ionized phase of gas with high metallicity and large kinematic spread like oxygen 6 ions. This complex multi-phase absorbing gas with distinct kinematic structure motivated us to reobserve this field in 2018 using KCWI. KCWI observation enabled us to find a new dwarf galaxy at the redshift of this absorber. This faint dwarf galaxy is only 27 kiloparsec apart from the quasar and only 21 kilometer per second redshifted from the massive distant galaxy. The KCWI footprint is shown with white rectangle on HSD image, and this newly found galaxy is marked with pink on all the figures. Here is the KCWI line map centered on oxygen 2 at the redshift of this newly detected galaxy, which is highlighting this dwarf galaxy. We have also modeled the image and emission line of the dwarf to study the properties of this galaxy, like its star formation rate and orientation. Given the low star formation surface density of this object, we do not expect significant outflows from this target. On the right-hand side, the rotation curve of the massive star-forming galaxy is shown in the top panel. The rotation curve is extracted using the ASI spectrum of this target, and we have also used a co-rotating thick disk model to obtain the rotation velocity through the halo along the quasar line of sight, which is shown in the bottom panel. We have also constrained the rotation direction of the dwarf along the quasar line of sight using its KCWI spectrum. The hatch region here shows the modeled rotation velocity of the massive galaxy, and this pink region presents the rotation velocity of the dwarf along the quasar sight line. By discovering the new dwarf galaxy at similar redshift as a previously known galaxy that was thought to be the only host of a CGM absorption system, we re-examined the absorption system and galaxy properties to discuss the origin of this multi-phase CGM, which is in a group environment. We have compared the absorption kinematics with galaxy rotation velocities as shown in this figure, looking for any connection between the host galaxy rotation and absorption kinematics. Again, here the pink represent the rotation velocity of the dwarf along the quasar sight line, and the hatch region, hatch blue region represent rotation of the massive galaxy. Given the expected rotation velocity of the dwarf along the quasar sight line is only consistent with this component, then the L1 component of magnesium-2 can be explained from a co-rotation scenario for the dwarf galaxy. Considering the kinematics of this component, as well as its very low metallicity, we concluded that the L1 component of low ionized phase of gas is accreting, most likely accreting onto the dwarf galaxy. However, L2 and L3 components of this phase are not related to any of these galaxies in kinematic space and could probably be a part of intergalactic gas transfer between these two galaxies like tidal stream or ancient outflows. Furthermore, based on statistics of a large sample of magnesium-2 absorption line, like MAGICAT, the dwarf resides at the ideal impact parameter to be associated to the observed magnesium-2 absorption in this system, with rest frame equivalent bits of 0.4 angstrom. We also put constraints on the possible origin of the high ionization phase of gas based on different evidences that I'm going to highlight the main ones here. This figure presents the distribution of oxygen-6 column density as a function of galaxy halo mass. This trend implies that the column density of oxygen is greatest around the halo mass of 10 to the 12, where the virial temperature of the halo is ideal for oxygen 6 ionization, and for lower and higher masses, the column density of oxygen 6 drops down. In fact, in CGM of higher mass halos, temperature would be favorable to produce higher ionization state of oxygen, like oxygen 7 or oxygen 8. In this figure, the dwarf that we call it G27 and the massive distant galaxy that we call it G163 are marked with the stars. Even though both galaxies are plotted at the same column density, the massive halo of G163 resides around the peak of this trend and most probably contributes the oxygen 6 components in this absorption system. The mass of the dwarf galaxy and its halo virial temperature is too low to contribute a significant amount of oxygen 6 column density. In addition, the presence of carbon 4 and a strong nitrogen 5 and oxygen 6 with broad velocity spread in this system, the supersolar metallicity of this phase of gas, and also the properties of massive galaxy, specifically its metal-enriched outflows, all lead us to the fact that the high ionized phase of gas is most likely originated from this massive star-forming galaxy. And finally, our work emphasizes the importance of performing component by component analysis whenever possible to disentangle the origin of CGM. And it also shows that sometimes the studies could suffer from incompleteness in their spectroscopic sample. Thank you so much for your attention, and I leave you with my summary. Please feel free to contact me if you have any question. Thanks again.